In the last chapter, we learned about the thermal processes and how when temperature is added to a substance, one of two things may happen. Either the temperature may increase and there is thermal expansion there, or there may be a phase transformation while the temperature is kept constant, like having ice melting into water or having water boiling into a steam. In this new chapter, we continue our discussion of heat and energy, and we move to learn about the laws of thermodynamics. There are two important laws that usually in physics we try to understand in order to have a better understanding for the world around us. The first law of thermodynamics is about energy conservation. So according to this law, we may add energy to any system, and as a result, one of two things may happen, or both of them. Either the internal energy will change, or the system may do work. Usually, the energy has to be balanced. We cannot gain anything for free. So if we are able to increase the internal energy or to do some work, then definitely there should be a supply of heat energy to the system. Then the second law is just a constraint on the first law. The second law will tell us which processes are allowed by the first law and which processes are not allowed. Like, for example, heat energy never flows spontaneously from a cold object to a hot object. In order for such a process to occur, we need to do work to carry the energy from the colder object to the hotter object. This is what we do in refrigerators and in air conditioning systems. So now we are ready to start formally our discussion for chapter 12. We start by considering this situation here. We have a cylinder, and inside this cylinder there is a volume of gas. The cylinder can move down or up. If it moves down, it will compress the gas. If it moves up, then the gas will expand. So there will always be some state of equilibrium. And the state of equilibrium is governed by the conservation of energy principle. But as we move from lack of equilibrium to equilibrium, we have always to apply the laws of physics that we learn in Physics 1. As we know in Physics 1, work is equal to force multiplied by displacement. So force, in this case, the force that's applied on the piston, multiplied by the displacement, delta y, this is equal to the work done on the gas by this external force that's pushing downward and compressing the gas. Now, from the relationship between force and pressure, we know that pressure equals force per unit area. So we can substitute for the force PA. P is the pressure and A is the area. So force per unit area is equal to pressure, or pressure multiplied by area is equal to force. So now the work is PA delta Y. This is the energy that can be transferred to a system This energy can be transferred by heat and also by work. So to do work, this is one way to add energy to the system. To heat the system, to supply Q amount of heat energy, that is another way also to change the energy content of the system. So here, when we substitute for A delta Y, the volume, we arrive at this important formula. Work equals minus P delta V. So we understand that in order to do work, we need to have a change in the volume. If there is no change in the volume, then the work will be zero. Consider this situation. In Physics 111, Physics 1, we learned about work as force multiplied by displacement. So here you have this force pushing to the right. You have this displacement. The object will be accelerated because of force. And the work is equal to the product of F by delta X, F along delta X. Now, keep this in mind and take the other situation here. So this guy is pushing on the piston with a force F, and you have this displacement delta X. So it's the same game. Also, we are doing work here. And as I illustrated earlier, this work will be E delta V. Now, the process in which the volume decreases do positive work on the gas. So when the pressure of the gas remains constant, P is constant, during the expansion or compression, this type of process is called isobaric process. Isobaric process. The pressure is kept constant. If you look to this graph, we call it the PV diagram. So the pressure is constant. The system moved from the initial state VI to the final state VF. So the volume is compressed from the initial value to the final value. Along this path, the pressure is kept constant. And we have this minus sign because the final volume is smaller than the initial volume under compression. So the change here, delta V, would be negative. Okay? So the work done on the gas is positive. When I say done on the gas, this means it's done by this external force, by those guys. Okay? The work done on the gas is positive. Another way to look to this situation so that you will not have a mistake in the sign, examine the direction of the force and the direction of the displacement. If they are along the same direction, then it is positive. If they are opposite in direction, cosine 180 degrees minus 1, the work would be negative. So here we are talking about the work done by the external force on the gas. This will be positive. But to complete the picture, if you want to examine the work done by the gas on the piston, the gas acts with a force that is opposite to the external force. So for the gas, the force is going to the left, but the displacement is still going to the right. So the work done by the gas is negative. But by the external source on the gas, it is positive. Okay? And always we calculate the work using the same formula, P delta V. Okay? Check your understanding. By visual inspection, order the PV diagrams. These are called the PV diagrams, pressure volume diagrams. So we are asked to order these diagrams from the most negative work done on the system to the most positive work done on the system. we have these 4 options. Any suggestions how we may proceed? I can give you a tip. We need to calculate PV. PV is the area under the curve. PV is the area under the curve. And as we do that, we need to pay attention to the direction of the process. Like this one, the volume here is increasing, while this one, the volume is decreasing. Here, the volume is increasing. Here, the volume is decreasing. So to answer this question, we need to do the math. So here, for this one, the work done on the system is negative 4 by 10 to the 5 joule, because now the system is expanding. If it was compression, it would be positive on the system. But because it is expanding, so now the work is done by the gas on its surrounding. The work done by the gas is positive, but the work done by the surrounding on the gas will be negative. For B, again, we have the area here for these blocks. We have here 2 and here 1, so it's 3 by 10 to the power 5 joules. And this is going to be positive because it's a decrease, it's a compression. For this one, it is an expansion, so the work done on the system is negative. The area is 3 by 10 to the power 5. And for this one, the work is positive, and we have 4 by 10 to the power 5. So to order them from the most negative to the most positive, this would be the most negative, A, followed by C, minus 4, then minus 3, followed by B, plus 3, and finally D, which is a plus 4.